Hi, this is Aaron Jerome again at Jerome Electronics. It has been a while since I have messed with the State Machines videos. I made the first two videos for State Machines about 8 months ago. Probably need to go back and edit and improve them. But then I got into the hectic school year, and I have been making all the other videos. I've made about 40 of them now. And now that I have, I've actually taught this to my students, and I've become a little more fluid in it, and so I thought it was a good idea to wait until now. Anyway, this is going to be State Machines Part 3, Idea to Equation to Simulation. This is where we're going to take a Mealy machine and build it. We've already made the state graph. We've already made the state bubble graph, and students should have this worksheet. So here's the state bubble graph. We've actually gone through that in the previous video. We have gone over the structure of the Mealy machine. Mealy kind of came up with this idea, which is the main foundation for all Mealy finite state machines. And now what we're going to do is take the idea. We're going to put the idea into a truth table. From there, we're going to simplify the truth table with K-maps, and then we're going to simulate the machine. We could actually build the machine on the multi-sim simulator, and it would actually identify the sequence of numbers from the stream of numbers. So here we go. What we're going to first do is eliminate the parts that we're not talking about right now, and acknowledging that we've already done the first part. We know that with three numbers, we're going to need three states, and that means we're going to need two flip-flops, because with one flip-flop, you only have two states, 0 to 1. With two flip-flops, you have, every time you add a flip-flop, you double the number of states. So that's 0 through 4 states. We will need 3 states, and so that's how the CSR is made. And that, you pretty much make that decision when you're putting together the bubble graph of what the CSR looks like, because it's just flip-flops. So, all right, so now I always put an index row on my truth tables, because as they get longer and I say, hey, let's look at row 7, it's easy for everybody to find, and we're all make sure that we're all looking at the same row. So I've got my rows indexed here. We're going to be building this. Well, we've got the current state register already on the screen, and we've talked about that. The next state decoder is what we're going to build next. I want to point out again, although I've probably done it many times in the previous video, to make the next state decoder, we need 3 inputs. We're going to need the regular stream of numbers input, then we're going to need inputs from CS0 and also from CS1. So the next state decoder figures out what the next state is, and this machine, when it's done, it will tell itself where to go next. So then it sends that data to the CSR, the current state register. So again, the NSD needs 3 inputs, the input I. So we're going to put that on our truth table, because that's one of the inputs. We're going to put that in the input section. I is a single bit, so we're just going to acknowledge that in that cell there. And the current state 0 is another input, so we're going to put that in there. And current state 1 is another input. Why are there 2 of them? Sometimes students ask. It's because the current state 0 and the current state 1, we need 2 digits to identify each of the states, because that's what it takes to count from 0 to 1 to 2. But also, we need to be able to feed the flip-flops 2 numbers. And so these 2 columns represent each of the flip-flops and the numbers we receive, and in the next column, the output column, it'll be the numbers that we send to them. So this column is also inputs. It's the CSS inputs, CS0 and CS1. Now, as usual, you already know what we're going to do with inputs. It's just a binary count, because that ensures that every combination has been addressed. And got the little gray line to separate the bits from the CS, or the inputs, the input stream, the number stream, from the CS0 and the CS1 because they are kind of different entities, but they are still all inputs. So we just numbered them accordingly. And you can number them vertically if you acknowledge that this is the ones column. This changes every other one. And this is the column weight. The twos column changes every two. And the fours column changes every four. But if you want to be considered a professional, you probably should get in the habit of numbering horizontally and then double checking your work with the vertical checks that we just talked about. Okay, so the outputs of the NSD are the NSS signals. This first box, the NSD, next state decoder, it decides what the next state is based on the inputs in our state graph, and it will tell the CSR what the next state is with the NSS signals, NS0 and NS1. So there's the next state output, and the next state 0 is one of the outputs, and another one of the outputs is next state 1. Those are the two feeds that go into the two flip-flops. Row 0 of the truth table. Here's what we're doing. We already know what we plan to do because we did that planning when we put together the state transition graph above, the bubble graph. So what we're really saying is row 0 of the truth table, that means we are in current state 0, 0. That means we are here. And from the number stream, we receive a 0. So if we're here and we receive a 0 from the number stream, that's that 0 right there. I'm going to say that again. So the data received is 0. And what is the next state? Well, that is, again, 0/0 as we go out. That first digit there before the slash is that 0. If we get that 0, that's what we do. So if we do, what's the next state? Well, it's going to be state 1 because we got the 0 that we wanted. And that means that we transition, or we transition the attention of the computer technically, to state 1. Okay? So that just means that is our intended state. If we are in state 0, we get a 0 from the number stream. We're going to transition the attention of the computer to state 1. Okay? So by this time, I encourage my students to work ahead of me if you understood that. If you don't understand that, here's another example. Here it is. We are, well, that is the example. But if we are in state 0, 1, that's where we are if we are here. And if we receive a 0 from the number stream, if we're here and we receive a 0 from the number stream, then that's the first digit here. Obviously, it's not the first digit to go to the next state. It's the first digit to go back to this state. Therefore, we are returning to this state. The next one. Now, you can pause the video if you want and work this out. I suggest you do, but I don't need to pause what I'm saying and wait for you. So I'm going to give you the solutions now. Warning, pause if you don't want to see them. Okay, the next one, if we are in state 1, 0, state 1, 0, or state binary 2, and if we receive a 0, 0, if we receive a 0, there it is right there, then we are going to transition back to state 0, 1. State 1, 1 does not exist. Therefore, even if it does get it won't get the number 0. And we haven't planned for it. We don't care what it is because it doesn't exist. Therefore, we're using the don't care wildcards here. We do that because, if you remember, they are very useful in K-mapping. Okay, so now we're going to do all that again, only we're going to go into state 0, 0 and figure out where to go next if we get a 1 from the number stream. Then we're going to do that with state 1, state 2, and state 3. Okay, so in this state, we are in state 0, 0 again, and we get a 1 from the number stream. The 1 isn't transitioning to the right, it's the transition above, meaning we go back to state 0, 0. If we are in state 0, 1 and we get a 1, that does transition to the right, not above. That means we have to transition to state 2. And so we're going from from state 1 to state 2 if we get a 1. If we are in state 2, there we are in state 2, it's the third bubble on the right, and if we get a 1, well, the 1 is the black arrow because I tried to code it with black arrows for the things we don't want. That's a 1. That means we're going back to state 0, 0, start over. And then there's state 1, 1. It doesn't exist, so we're going to just use the wildcards for that. So we have figured out what we want the next state decoder to do on the Mealy State Machine. One more thing we might do is work on the output Z. Or in other words, we're going to figure out the logic that will go into the output decoder. And Z, of course, is a report of a 1 if we got the sequence that we're looking for. Okay, so we're going to figure that out. To figure out what Z is, it consists of a single bit of data right there. So Z will be a single byte, 1 if we've successfully found the sequence, and 0 if we have not. That it requires 3 inputs. In fact, if you look carefully, it requires the exact same 3 inputs for the output decoder that the next state decoder got. It needs a copy of the input stream, and it needs a copy of CS0 and CS1. So we still need the 3 same inputs. What we don't need, we'll need input I, and we're going to need input current state 0, CS0, and we're going to need CS1. And NSS, though, this column NSS, that is an output, an earlier output. We don't need that to calculate the output decoder, so we'll hide that for now. Okay, so this Z, these Z values are very easy because there's only one time and place when we have had success. That's the 1 if we get a 1 after 0, 1 was found in state 2. The rest of them are going to be zeros, or if the states don't exist, they're going to be X's. So we're going to find the 0 at row 0. So just doing the same thing we did before, only this time for the output decoder. If we are in state 0, 0, that's here. And if we get from the number stream a 0, then what is the output? Well, the output is the thing on the other side of the slashes on the transition these transition arrows. It's something slash something. And so if we're in state 0, 0, and the input happens to be a 0, then the state graph shows that the output is a 0. That is the output on the other side of the slash every single time. And if you look at them all, they're all zeros there except for that one state, that one transition where the output is 1. That's success. That means party time. We found the sequence. And so that is going to be a 0 there. And if you should probably predict the rest of them, but I pretty much told you what the rest are. The 1 output is only going to be after state or in state 1, 0, and if we receive a 0. So here, that's state 1, that's a 0, that's what we have. It's a 0 there. Here we're in state 1, 0, and we receive a 0, and if we do, then the path we're going on has a slash, has a 1 on the other side. That's where that success 1, we found the sequence 1 is. State 1, 1 doesn't exist. We just put a wildcard don't care there, and because state 1, 1 doesn't exist. But they are useful later in K-mapping. Doing that all over again for each of the states, but since we know the 1 is only in one place and the rest have just zeros after, we know the rest are zeros. And we could actually look at them. Of course, state 1, 1 doesn't exist, so that is another wildcard. Okay, so now we have completed all the inputs and all the outputs of our truth table. And so next, there it is, we've done it. We can ditch the state graph. We don't need that anymore. The next step is to simplify the truth table, and we're going to do that using K-maps. So here's your worksheet. This is what your worksheet should look like so far, and here are the 3 K-maps. I need to make a little more space on my screen your worksheet should have enough space, but I'm making enough space on mine so that I can demonstrate, so I can show how the K-maps work. On the current state register, we have NS0 and NS1. Those are what's going to feed the first and second flip-flop inside the CSR. And out of that comes CS0 and CS1. And of course, on the other down below will be not CS0 and not CS1, and we'll talk about those. But we're going to simplify the NSO column so we know what to feed into the flip-flops as NSO. And of course, the NSO column is here. And I'm putting tails on the truth tables because CS0, CS1, all that stuff is too much information to try to fit above the squares. Also be aware, and this is instead of putting CS1 and CS0, we're just going to put the values of them and in numerical values. So I call this double knot, left knot, no knot, right knot pattern, which is always on K-maps. And of course, under the tail, I'm putting the input, and I'm putting I equals 0, which really is just not I, and then I equals 1, which is I. There's something else that's really important here that I try to point out every time I use a K-map, and that is where you put the very first input sensor, the input information, the very first one. In this case, it's I, the first column. Wherever you put that determines the direction that you populate the K-map. The population of the K-map always goes away from that very first input variable. Since I put it under the tail, it's on the side, it's here. That means we're going to populate it horizontally. If I had put the I's above, then I would be populating it vertically. Just that saves time. So now we're going to populate it. What I'm doing is just looking at the first four, 1, 1, 1, X, and I'm putting that into the K-map, remembering to skip the column and then go back. Doing it again with the next 4 digits, and that is 0, 0, skip 0, go back, X again. And if you remember now, what we do is we implicate the biggest groups we can. Well, that truth table is only 8 cells, and we cannot implicate all 8 because that would include zeros, and we don't implicate by including zeros with minterms. So what can we implicate? We can't do a group of 8. Can we do a group of 4? Oh yeah, we can. We can do the entire top row because the X can be considered to be a 1 if it's useful. So that does another thing. If we ever get an entire row implicated, it cancels everything above, which means that the result of that implication is just not I, because I equals 0. So we're done with this one because there aren't any unimplicated ones, and so we can do the next one. And the next one is going to be NS1, and I've just populated real quick the outside of the K-map, and I suggest you stop the video and see if you can populate the input, implicate the inputs in the cells, and figure out NS1 before I do. So if you're going to stop the video, do it now. Okay, the inputs 0, 0, 0, X, 0, 0, skip 0, go back X. Then 0, 1, 0, X, 0, 1, 0, go back X. We have to implicate the 1 in the biggest group possible. Turns out the only thing we can do is implicate it in a group of 2. That group of 2, over on the side, we're going to have to keep I as I equals 1, or I. And then above, we can cancel something. On the side, there's nothing to cancel against, but above, we have a set of opposites on the left. This 1, which is on the left, which means it's CS1, and this 0, which is on the left, which is also CS1, are opposites. Therefore, they cancel out, and so our result is going to include I, and also the thing on the right, which is CS0. So that is the simplification for NS1. So now we have the ability to build the logic for NS0, which we will plug in here, and we will build the logic with AOI gates in the NSD, and we'll do the same thing for NS1. Here's the logic for NS1, and we'll plug that into the second flip-flop after we build that logic with the logic gates. Okay, now we have Z here. We need to simplify the Z column, and hopefully you maybe have done that already, but if you haven't, pause the video now and hurry and fill those in, and then start the video again. Okay, populating the Z, that's going to be 0, 0, skip 1, 1, go back X for the first 4. The last 4 are 0, 0, 0, X, 0, 0, skip 1, 0, go back X. And we want to implicate the largest group we can, which is the 0 and, which is the 1 with the X, so that's a group of 2. We have to keep the not I in the equation because it has nothing to cancel against, because nothing on this row has been implicated on the lower row. And then on the above, it looks like the thing on the right, the values on the right are opposites, and that represents the CS0, which means CS0 will not be used in the solution, but CS1, which is both ones, will be used in the solution. So here, the resulting simplification is not I times CS1. Okay, so I have eliminated the K-maps because these are the equations we need to build the logic inside the NSD, the next state decoder, and the OD, the output decoder. And so I'm just moving things around on mine. You should have enough space on your paper to do this on your worksheet, but moving things around to help me remember what I want to build into my NSD, my next state decoder. And the inputs for that are going to be I, the input, the number stream that's fed into here, so it can recognize every sequence of 0, 1, 0. And then we're also, according to Mealy, we need to include CS0 and CS1 as inputs. So now I'm going to build the logic in here, and then I'm going to send that result to NS0. If you look above, NS0 is just not I, meaning we need to put a NOT gate right there, and then we're done for NS0. For NS1, it says we also need a copy of I, but not knotted, and we're going to multiply that with CS0. So now we're done with NS1. Well, what does that mean for CS1? It means we're not using it. We're just going to cap it off and not use it, even though we ran it over there. In fact, we could actually eliminate that entire signal that returns back to the NSD, but I'll just leave it there. Okay, so now we plug the NS0 into the first flip-flop at D input, data input, and the NS1 into the second flip-flop into the data 2 input. And now we can build the output decoder. The output decoder requires a copy of I that is knotted. It will also use CS1, and so the CS1 I positioned the output decoder across from CS1 so that it can just be plugged right into it. And there's my copy of I. It's not hooked up to the number stream yet, but we will in a minute. And then of course, once we have the logic in output decoder, it will result as the Z, giving us a 1 if we found the 0, 1, 0 sequence, and otherwise it'll always be a 0. So we need a AND gate to multiply the NOT I and the CS1, hooking up the CS1 to the AND gate, using a NOT gate or an inverter to invert I, the number stream, and we put that into the AND gate. So now we probably ought to patch that I over to the original input number stream. And a couple more details, hooking up CS1 to the flip-flop. That's where CS1 comes out. I did run a signal over to CS1 on the other side, but we're not using it, so really I've just erased it again. You don't have to put that in there. Now CS0, that needs to go into the inputs. as it shows on the Mealy machine pattern above. So that is plugged in. You could go in right now and build this in Multisim. I think it's pretty much done. Oh, I always forget. Flip-flops are not flip-flops unless they have a clock input. Otherwise, they're just latches. This thing needs some kind of a pulse to keep it going, and that's the clock. So I'm hooking up the clock. And then one other thing that I probably should do, well, I absolutely should do. Notice that we have presets and clears, which are really just direct connections to the SR latch inside there. But if we invoke either preset or either clear, we're overriding what the clock wants. That would be a more sophisticated result. But what I would do is just, since they're all active lows, because they all have that little bubble, meaning they're controlled by zeros, I would connect them all to just the VCC power, meaning that you give them all a 1. You have to give them something or the thing won't work. But hook them all up to 1s, and that says to the flip-flops you don't intend to use the overrides for now. Okay, so that's the Mealy State Machine, and we have used it to identify a pattern of numbers. Of course, you remember, hopefully, that state machines can do many things. They are a very useful type of a controller. We've talked about vending machines, garage door openers, traffic lights, card readers. We saw, I think earlier we saw where they can automatically, without human intervention, reserve a room in a motel or a hotel. Okay, so that is the Mealy State Machine, and that is the end of this video. And when we go to the next video, we're going to talk about proof of concept waveform analysis. So we'll continue with part 4.